Welcome to this lecture on propositional logic, focusing in particular on representation. During this lecture, we'll cover what propositional logic is, the basics of propositional language, propositional truth, the concept of equivalence, and the basics of logical calculation. Recall from our Introduction to Artificial Intelligence lecture that two of the key concepts behind artificial intelligence include knowledge representation and reasoning. Knowledge representation is aimed at transforming information from the real world into a format that a machine can use for tasks such as reasoning, learning, problem solving, and understanding. Also, recall the different knowledge representation strategies that we indicated we'd cover in this course. We've already taken a look at trees and rules, and now we're moving into logical representations, including propositional logic and first-order logic. And we also talked about major types of reasoning, including deductive, inductive, abductive, and analogical. Remember that deductive reasoning is all about utilizing a general rule to draw specific, certain conclusions. And also in our Introduction to Artificial Intelligence, we covered some of the basics of logic, including its goals of representing knowledge of the world and reasoning with that knowledge. We noted that logic is arguably the most important approach to knowledge representation, and that a logic, almost by definition, has a well-defined syntax and semantics, as well as being conserved with truth-preserving inference. We also took a look at logical arguments, which include a finite set of statements consisting of premises as well as a conclusion. We discussed the difference between valid and invalid arguments, which focused on whether or not the argument had a correct logical structure. We discussed the difference between sound and unsound arguments, where sound arguments are both valid and had premises that were actually true. We introduced syllogistic logic and well-formed formulas, and we defined the syllogism as being arguments of two or more well-formed formulas in which each letter occurs twice and the letters form a chain of logic. Moving on to the content of the current lecture, why learn about propositional logic? This topic provides the skills needed to more easily work with, manipulate, and reason with more complex knowledge and tasks. You can think of this as learning the calculus skills needed for reasoning. As we've reviewed, syllogistic logic is a system of reasoning used by ancient Greeks that examined the fundamental principles of logical transference. In other words, if A equals B and B equals C, then A equals C. Propositional logic builds upon syllogistic logic. In our first section of this lecture, we'll discuss what is propositional logic. First off, let's define a proposition as a declarative statement that's either true or false, but not both. A proposition can also be referred to as a formula. An atomic proposition is the most basic form of proposition. In other words, it's a fact where the truth or falsity of that fact doesn't depend on any other propositions. Here are some examples of propositions. The statement 1 plus 1 equals 2 has a value of true. The statement 1 plus 1 is greater than 3 has a value of false. The statement Allison likes patient care also has a value of true. And the statement Ryan has an MD is also false. Conversely, the following statements are not propositions. For example, the formula 1 plus 1 is greater than x doesn't have a truthfulness that can be determined. So this is not a proposition. The statement, "What a great book," is an opinion, and also doesn't have a clear truth value. The statement, "Is your car red?" is a question, and again doesn't have a truth value. Of note, a paradox is a statement that cannot be assigned a truth value. Therefore, a paradox cannot be a proposition. Here's an example, also referred to as the liar paradox. This statement is false. Considering that statement, it's clear that it can neither be true or false. Therefore, it is a paradox. So now let's define propositional logic. First off, it's a formal modern logic. It can also be referred to as Boolean logic, symbolic logic, propositional calculus, statement logic, or zeroth order logic. As mentioned, it relies on the principles established by syllogistic logic. Propositional logic is concerned with truth and falsehood, or more specifically, how truth values extend through a series of propositions. For example, consider the statement, "Ryan is the course director," and "Ryan is a magician." Both of these individual statements are propositions. and each have their own truth values, where in this case, the first is true and the second is false. When put together, this statement as a whole is false, because I am not both the course director and a magician. Propositional logic allows us to build up more complex statements, also called sentences, by combining propositions with logical connectives. This is the foundation of the syntax of propositional logic. Now let's learn more about the propositional language, including its syntax and semantics. First, let's learn about variables in propositional language. To formalize atomic propositions, we use simple symbols. These are known as propositional constants. These symbols inherit the same truth values as the original statements. So for example, the statement 1 + 1 = 2 might be represented by the symbol p, which inherits the same value of true. Of note, there are a couple reserved constants. For example, capital F is a symbol that always represents false, and capital T is a symbol that always represents true. Note that a propositional signature is the foundational set of symbols, in other words, propositional constants, used to build logical formulas. You can think of a propositional signature as being the alphabet or set of building blocks for your logical formulas. For example, if this box included all of our available propositions, then our propositional signature would include the symbols P, Q, R, and S. Now let's learn about connectives. These are also called logical operators. Here we see the full set of connectives. The first is conjunction, which can be represented by any of these symbols. The preferred symbol that we'll rely on in this course is given in red for each. The conjunction connective refers to and. The disjunction connective refers to or. The negation connective refers to not. The implication connective refers to if, then, connecting two propositional constants. And lastly, there's biconditional, which can be conflated with and equals, but is notably different, instead meaning if and only if. Now let's define a propositional sentence. This is a statement obtained by using connectives to combine either members of the propositional signature, for example, connecting the propositional constants P and Q using the and symbol, or a propositional sentence can also combine a compound expression formed from members of the propositional signature. This allows for formation of more complex sentences. Here we have an atomic proposition Q combined with a more complex proposition of S or P. Together, this reads S or P and Q. Next, we'll cover truth tables. These describe the behavior of a proposition under all possible interpretations of the atomic propositions included. While this sounds complicated, it's actually pretty simple in the end. When we're talking about atomic propositions, we're talking about the most basic true-false propositions represented by propositional constants. For example, P or Q as seen in this table. The length of a table is based on the number of atomic propositions that we're considering. Given n different atomic propositions, a truth table can have 2 to the n different rows in the truth table. This is because each atomic proposition can take one of 2 values, true or false. Let's walk through an example. Here we have 2 atomic propositions. Steve likes cakes is represented with a P, and Steve eats cakes is represented with a Q. These 2 atomic propositions become the first 2 columns of our truth table, and our rows examine every combination of true and false that these propositions can have. As we'll explore later, we can also add other propositions to this table based on these atomic propositions in order to work out their truthfulness. For example, in this table we've added the propositions not P and not P or Q. For not P, notice that when P is true, not P is false, and vice versa. This is our first simple example of how truthfulness gets propagated through the truth table. We'll be using this truth table concept to better understand connectives in the following slides. First, let's take a closer look at the conjunction connective, also known as and, which is represented by this symbol. This indicates that something is true only when both propositions being connected are true. Let's use the example P and Q, which might translate into something like Steve likes cakes and Steve eats cakes. Let's examine our truth table to see the results of the AND connective. Specifically, the only time P and Q is true is when the atomic propositions P and Q are both true. Otherwise, it's false. We can also examine this visually with a Venn diagram. We have two circles that represent P and Q, and the conjunction P and Q represents this middle section in red, used here to describe where truth occurs. Now let's look at the disjunctive connective, also known as OR. This is represented by this symbol. A disjunction indicates that something is false only when both propositions being connected are false. Let's use the example P or Q, which might translate to something like Steve likes cakes or Steve eats cakes. Examining our truth table, we see that the only time P or Q is false is when both P and Q are false. Otherwise, P or Q is true. This is because you only need one true in either column. Here is the Venn diagram describing truthfulness using a disjunction, where it's true if either P or Q is true or both are true. Now let's look at negation, also referred to as not. This is represented by this symbol. Unlike the other two connectives we've talked about so far, not only applies to one proposition at a time, and not is simply the inversion of truth. Examining our truth table, when we have false for P, it becomes true, and vice versa. This might translate to Steve doesn't like cakes, or not Steve likes cakes. Next, let's look at the slightly more complicated implication connective. Here we have if something, then something, represented using this arrow symbol. It can also be read as P implies Q, rather than if P then Q. An implication is true whenever the if proposition is false, or when the then proposition is true. Examining our truth table, we have the example P implies Q, which could translate to if Steve likes cakes, then Steve eats cakes. We can see that this implication is true whenever P is false, or when Q is true. Therefore, the only situation in which P implies Q is false is when P is true and Q is false. Here's the Venn diagram for implication. Again, we see that this is only false when P is true, but Q is false. Digging into implications a bit further, let's think about what it means to have sufficient and necessary conditions. When you have P implies Q, P is called a sufficient condition for Q, but Q is a necessary condition for P. Let's look at a couple natural language examples of this to try and make this clearer. First, note that being a cat is a sufficient condition for being a mammal. This is equivalent to saying if an animal is a cat, then they will be a mammal. However, being a mammal is a necessary condition for being a cat. Therefore, if an animal is not a mammal, they cannot be a cat. Let's also take a moment to define converse, contrapositive, and inverse. Starting with the implication if P then Q, we can describe new conditional statements. If we have the statement if Q then P, this is called the converse of our original implication. If we have the statement if not P, then not Q, this is called the inverse of our original implication. And if we have the statement if not Q, then not P, this is called the contrapositive of our original implication. Here's an example starting with another original implication. If it is snowing, then I will not go to school. The converse would be, if I do not go to school, then it is snowing. The inverse would be, if it is not snowing, then I will go to school. And the contrapositive would be, if I will go to school, then it is not snowing. Lastly, let's look at the biconditional connective. Again, this means if and only if, and is represented by this symbol. The biconditional is true if P and Q are either both true or both false at the same time. Here's the truth table with the example P biconditional Q, which might translate to if Steve likes cakes, then Steve eats cakes, and vice versa. Note how P biconditional Q is only true when the atomic propositions P and Q are either both false or both true. Here's the Venn diagram describing the biconditional. We can see that something is only false when either P alone is true or Q alone is true. Now let's get into the grammar of propositional language. First, let's define an abstract proposition. These are more general than atomic propositions. They can be any syntactically correct proposition, otherwise known as a well-formed formula. Here are some examples of abstract propositions. You can nest complex propositions as deeply as needed, but parentheses might be needed for grouping in order for them to be interpreted correctly. Here are some examples of incorrect abstract propositions. For instance, an atomic proposition with the and connector alone, two implications and an atomic proposition, and the not connective combining two propositions. In general, you want to omit as many parentheses as possible, but without causing ambiguity in the expression's interpretation, much like we do in algebra. As we'll reiterate in a minute, negation has the highest priority. Here are some examples of simplifying abstract propositions without losing their original meaning. In this first example, we can sequentially remove the parentheses without losing the original meaning. And the same is true in this second example. But this last example incorrectly simplifies the abstract proposition because the negation operator has the highest priority. Therefore, these parentheses can't be removed without changing the meaning of the expression. Here's a summary of the precedence of logical operators. This is similar to the concept of precedence of symbols in mathematics. As I said before, the negation operator has the highest precedence. This is followed by and, or, implication, and lastly by conditional. As an illustration of logical operator precedence, consider that the propositional sentence P or Q implies not R is equivalent to the sentence P or Q in parentheses implies not R. However, if the intended meaning of the sentence was P or parentheses Q implies not R, then parentheses must be used to clearly indicate the intended interpretation. Now let's dive into propositional truth. Here we revisit and learn to compute truth tables. Let's say we want to compute the truth table for this propositional sentence. P or Q implies not R. First, we include all the atomic propositions found within it, in this case, P, Q, and R. Note how the number of rows in the table are determined by the number of unique combinations of true and false among all three atomic propositions. Next, we add each non-atomic proposition to the truth table. For this, we'll use our respective rules for connectives, and the order in which they'll appear in the truth table will be determined by the rules of precedence. So in this case, not R has the highest precedent, and so we add it first to the truth table. Note that the truth values for not R are simply the inverse of those for R. The next highest precedent goes to P or Q. Again, we follow the rules for a disjunction connective, where the truth table values are false only when P and Q are both false. Lastly, we combine these two expressions together using the implication. We can fill in the truth values for the final proposition by relying on the truth table rules for the implication. Specifically, we'll only get false when the if part is true and the then part is false. We can see situations where this proposition is false here, here, and here, where P or Q is true and not R is false. Now let's talk about interpreting truth tables. Every row in a truth table is a possible interpretation, otherwise known as a model. Interpretations are basically possible worlds. Finding the possible truth values of the constituent propositions gives us the meaning of the sentence. The term propositional interpretation refers to truth mapping of propositional constants, such as these three atomic propositions: is it snowing, true or false? There's a hurricane, true or false? Or is there a school day today, true or false? Sequential interpretation is truth mapping of propositional sentences, such as the example we gave in the last slide. Let's examine a single interpretation or model found in this truth table, specifically this row indicated by the red arrow. We could interpret this line as saying that it is not snowing, but there is a hurricane, therefore there isn't school today, which is based on the propositional sentence P or Q implies not R. We could also represent these interpretations or models with a tree. Here we have a different propositional sentence, also known as a formula. specifically not A and B, biconditional C. The model is our interpretation, where here 1 represents true and 0 represents false. Similar to the truth table, we can start with our lowest leaves of the tree being our atomic propositions, and their values of truthfulness. In this model, A is true, B is true, and C is false. We can use this tree to examine truthfulness as it builds up towards our complete formula. So starting from A, which in this model is true, it becomes false when negated. Then not A and B also gives us false, because not A and B are not both true. Lastly, we have not A and B if and only if C, which is true given that both not A and B, as well as C, are both false. Now let's describe some properties of abstract propositions. First, we have valid propositions, also known as tautologies. Here, every interpretation is satisfied, in other words, true. Then we have contingent propositions. This means that some interpretations satisfy it, but others do not. And lastly, we have unsatisfiable, which means that no interpretations are satisfied or true. A tautology is an abstract proposition that is always true. In other words, the sentence, heads I win, tails you lose, which always has to be true. Another example is, this course is easy, or this course is not easy, which also by necessity always has to be true. Here we represent that statement with the propositional sentence, P or not P is equivalent to always true. If we look at a different example of a proposition that is a tautology within this truth table, we'll notice that every single row is always true, represented here by all ones. On the other hand, a contradiction is an abstract proposition that is always false. For example, the statement, this course is easy, and this course is not easy, which of course is a contradiction since both things can't be true at the same time. Therefore, this statement is always false, and we can represent it with the propositional sentence, P and not P is equivalent to false. Looking at a different example of a proposition that is a contradiction in this truth table, we see that all interpretations or models are always 0 or false. Lastly, we define contingency. This is an abstract proposition that is neither a tautology nor a contradiction. Here are some examples of abstract propositions that would be considered contingencies if you work them out in a truth table. Next, let's move on to the concept of equivalence, where we further explore the calculus of logic. Equivalent propositions are abstract propositions with identical columns in a truth table. Another way of thinking about them is that they have matching truth values across every model or every interpretation. We can see an example of 2 equivalent contingencies in the truth table below, here and here. Specifically, not if A then B, and not A or B. Note that both of these contingent propositions have the same truth values for every row. This indicates that these propositions are equivalent. Of note, by definition, all tautologies are always equivalent to one another, and separately, any contradictions are always equivalent to each other. Let's look at some natural language examples of equivalent propositions. In the first case, Alice is not married, but Bob is not single. This is equivalent to the statement, Bob is not single and Alice is not married. Only the order has been changed here. Yet another equivalent statement to these is neither Bob is single nor Alice is married. All 3 of these statements are equivalent, as can also be demonstrated by the truth table below, where the truth values for all 3 interpretations are the same. Note that the symbol comprising of 3 horizontal lines often is used to denote equivalence, as we've already seen used a couple times in this lecture. But before we move on, let's briefly look at some extended notation that we'll use for much of the remaining lecture. Whenever 2 propositions are equivalent, we'll express this using this symbol instead, which looks like an equal sign with the word val on top. We'll use this in place of the 3 horizontal lines we've seen previously to denote equivalence. This symbol is not part of the language of abstract propositions, but we're going to use it here as a meta symbol. As an example, these 2 abstract propositions are equivalent. Therefore, we use this symbol to relate their equivalence. For the rest of this section of the lecture, we will examine a number of standard equivalences. You can think of these as transformation rules, much like you'd use in algebra or calculus to transform and/or manipulate equations to make them easier to work with or to create proofs. The first one we'll look at is commutativity, which includes the following. P and Q is equivalent to Q and P. P or Q is equivalent to Q or P. And P by conditional Q is equivalent to Q by conditional P. So far, these are all quite straightforward. Note that biconditional is not the same thing as equivalent. Also, note that P implies Q is not equivalent to Q implies P. We can verify this with the truth table here. Next, we have the equivalence of associativity. In this first example, we just show that we can move the parentheses when we have a string of ands, and it ultimately means the same thing. So P and Q in parentheses and R is the same thing as P and Q and R in parentheses. The same is also true for ors, and the same is also true for the biconditional. Again, note that this doesn't work for implications. And again, we prove this with a truth table. When we have associativity occur, we can just write P and Q and R instead of using these parentheses. In case you're not familiar, the abbreviation NB denotes Latin academic notation that translates to note well, which indicates something that readers should pay special attention to, such as a critical assumption. Now let's examine idempotence and double negation as standard equivalences. Idempotence basically says that if you have the same proposition connected by an and, it's the same thing as having that proposition just once. The same is also true for ors. However, P implies P is not equivalent to P alone, and also P by conditional P is not equivalent to P alone. But of note, P by conditional P is equivalent to true. This is because P will always have the same truth value, therefore the value of P by conditional P is always true, which also means that it is a tautology. Double negation is also straightforward. If you have two negation values next to a P, they can be reduced to P alone. Basically, this is like a double negative, such as, it is not that I don't like spinach, which means the same thing as I like spinach. Our next standard equivalence is adsorption. This is also known as simplification or reduction. In this example, we have P or P and Q, which is equivalent to just P alone. Also, when we have P and P or Q, this is also equivalent to just P alone. There are also standard equivalences that are basically simplifications of abstract propositions down to truth constants. With inversion, we have negate true is equivalent to false, and negate false is equivalent to true. Contradiction is where we have P and not P, which is always equivalent to false. The excluded middle is when we have P or not P, which is always equivalent to true. Negation indicates that not P is always equivalent to P implies false. And lastly, here are some equivalences for true-false elimination. P and true is equivalent to P. P and false is equivalent to false. P or true is equivalent to true. And P or false is equivalent to P. Our next standard equivalence is distributivity. This is similar to what we learned in early algebra, where here the AND connector is treated like multiplication, and the OR connector is treated like addition with respect to how this equivalence works. Specifically, P and Q or R is equivalent to P and Q or P and R. Notice similarities with this algebraic equation below. Further, P or Q and R is equivalent to P or Q and P or R. Our next standard equivalence is called De Morgan's law. Here we have not P and Q is equivalent to not P or not Q, or also not P or Q is equivalent to not P and not Q. Focusing on this first rule, we have the truth table demonstrating the equivalence of both propositions, not P and Q, and not P or not Q. Of note, this rule is also foundational to logic gates in circuits. Next, we have the implication and contraposition standard equivalences. Starting with the implication equivalence, if P then Q is equivalent to not P or Q. On the right, we can see our first example of how we can use these equivalence rules to transform logical expressions. Starting with not P implies Q, we can apply the implication equivalence to yield double negate P or Q. We can then apply the double negation equivalence to yield P or Q. Ultimately, this means that negated P implies Q is equivalent to P or Q. Next, we have the contraposition standard equivalence. P implies Q is equivalent to not Q implies not P. Note here that P implies Q is not equivalent to not P implies not Q. And lastly, we have the by implication and self-equivalence standard equivalences. The by implication equivalence says that P by conditional Q is equivalent to P implies Q and Q implies P. The self-equivalence equivalency simply says that P by conditional P is always equivalent to true. This slide collects all of the equivalences we've covered so far. You're likely to find them useful to have in one place when you're trying to conduct calculations with equivalences, much like having a cheat sheet for the rules of algebra. Take some time to review these equivalences and consider using truth tables to prove their equivalence. In this last section of the lecture, we'll briefly introduce logical calculation. Here, we're talking about the calculus of logic. Recall the example calculation we saw earlier, where we started with negate P implies Q, and showed that it's equivalent to P or Q. This calculation was meant to answer the question, can we conclude that negate P implies Q is equivalent to P or Q? And in fact, we showed that it was. Some other basic equivalences to note here include reflexivity, symmetry, and transistivity. Reflexivity indicates that a proposition is assumed to be equivalent to itself. Symmetry indicates that if the proposition P is equivalent to Q, then similarly the proposition Q is equivalent to P. And lastly, transitivity indicates that if P is equivalent to Q and Q is equivalent to R, then P is also equivalent to R. Diving more into logic calculus, let's talk about substitution. This is the replacement of all occurrences of a letter by a formula. For example, let's replace the letter or atomic proposition P with the formula or more complex proposition Q and P. Specifically, we'll do this within the following equivalence statement. Given this equivalence, we make our substitution such that we get this new equivalence, where P has been replaced by Q and P. Substitution says that this expression is still equivalent to this one. This would also be true for some substitution of Q, or for both P and Q simultaneously. In other words, substitution preserves equivalence. Next, let's introduce Leibniz's rule. This is the replacement of a subformula by an equivalent subformula. For example, P implies Q, highlighted in blue, is equivalent to negate P or Q, highlighted in green. Knowing this, we can make new valid equivalences where we substitute the blue portion with the green one to give us this new but equivalent formula. Now let's apply our logic calculus to prove some tautologies. Specifically, let's prove that negate P and negate P is a tautology. Recall that to prove something is a tautology, we need to prove that it always has the value true, or that the proposition is equivalent to true. Starting with our target formula, we can apply equivalence laws to transform it. First, we apply De Morgan's equivalence, shown here on the right. This lets us transform our starting formula into this next one, which is equivalent to the first. Now we can apply double negation, shown here on the right, to further transform this expression into this one, which is also equivalent. Lastly, we can apply the excluded middle to also show that this expression is equivalent to true. At this point, we've demonstrated that our original formula is equivalent to true. Therefore, our original formula is a tautology. Here's another example where we'll try to prove that a formula is a tautology. For this, let's notice that there's a biconditional in this formula. Therefore, We can demonstrate that this expression is a tautology if we can show that both sides of the biconditional are equivalent to one another. So let's try to prove that not Q implies R is equivalent to not R and Q. Starting with not Q implies R, as before, we apply a series of appropriate equivalence rules to transform the propositional sentence. Our first step uses implication in concert with Leibniz's rule so that we can ignore the negate on the outside when we do this transformation. Next, we use the De Morgan equivalence along with the substitution rule to do our next transformation. And lastly, we apply double negation. This leaves us with the same proposition that was on the right-hand side of our original biconditional, therefore demonstrating their equivalence. Thus again, we've proved that this whole formula is a tautology. Here's another way of putting this conclusion. From the fact that the left side of the formula is equivalent to the right side of the formula, it follows that this whole formula is a tautology. To summarize what we've covered in this lecture, we began by learning the language of propositional logic as a form of knowledge representation. This included atomic propositions, which are simply symbols with a fixed meaning, that are notably not variables. We also examined connectives, such as and, or, if then, etc., and how they transform truthfulness across a propositional sentence. We also introduced truth tables, tautologies, and contradictions as important concepts for summarizing truth and falsehood across a propositional sentence. We also discussed equivalences, illustrating how separate propositions can mean the same thing, and thus can be exchanged for one another. And lastly, we introduced logical calculation, where we utilized equivalences to demonstrate logical proofs, such as proving that a given proposition is a tautology. We'll end this lecture with a quote by Lewis Carroll from Through the Looking Glass. "Contrariwise," continued Tweedledee, "if it was so, it might be, and if it were so, it would be. But as it isn't, it ain't. That's logic." I'm Reiner Benowitz, and thanks for joining me for this lecture. Stay skeptical, curious, and creative.